Okay, guys, before we actually continue, regarding your assignment, I think you're supposed to know what to do. This relates to example 5.4. Okay, I wanted to tell you or catch up a little bit, some things because I need to address certain issues here. Okay, so let's see, the exercise 5.6 again, 5.4 again. Okay, where basically having autoregressive stationary, supposedly stationary process. Okay, now for time. Okay, so if you have the time here is starting at this is the time 1, 2, 3, 4, 5, and 6. Okay, now these are the observation of the process that you have. Okay, so basically you have yt. Okay, so t is the time. Okay, so the observations of the process are, okay, and that's what you have: 0, 3, 5, 2, 0, and 5. Okay, so this is the observation of the process, and here you're going to have yt minus 1. Okay. Alright, so yt minus 1, this is the lag version of the process. Okay, what I'm talking about here is you're supposed to estimate. Okay, so basically the model is yt is equal to the constant plus a times yt minus 1 plus the noise. Okay, so then basically the lag version, if this is the time 1, so that could be the observation of the process at time 0, which is not there, so that is missing, of course, right? And here you have, this is the observation of at time 2, so if t is equal to 2, then the observation is 3, and if t is equal to 2, then you have t minus 1, which is equal to 1, so this is going to be t1, so this is 0, right? Alright, so that's how it continues. Okay, so then you get 3 here, then you get a 5 here, 2 here, and 0 here, and basically it stops there. Okay, so it's no longer there because there is no such thing as time 7, but you can also add that here to it, so if you like. Okay, so then basically it will be 5 here. Okay, but again, the observations are not there. Okay, so the sample, this is the sample, guys. Okay, so that's a sample, that's the one. Okay, this is the sample observation that you have. Okay, and again, here are the observation pairs. These are, let me just put more emphasis on them. Okay, so you have basically 5 observation pairs if you have a sample of 6. Okay, so if you have a sample of 6 observations, then you just have like 5 observation pairs, not more. All right, so you have to take that into consideration when implementing the program. Okay, because basically, this is the regression that you have to perform. So you have to regress. Basically, this is the dependent variable. Okay, so the observations of the dependent variable, and this is the observation here, basically, of the explanatory variable. Okay, so you have 5 observations of the dependent variable and 5 observations of the explanatory variable, meaning that you have 5 observation pairs of the two. Okay, all right. So that's how it works, basically. Okay, so if you basically know how what to do when regarding the we did this last time, so I'm not gonna repeat this again, but the regression line, or basically the regression model, let me just do it like this. Okay, so this is, okay, so after performing certain calculations, okay, so yt hat is going to be equal to, and then what I got as a result is, okay, so you have negative 5 over 18 for the constant. No, sorry, this is the constant is something else. Sorry, this is not negative. The constant is not negative because the process here just has positive observations, so it cannot be negative, because then otherwise the mean would be negative as well. So mean would be estimated as such. Okay, so then you have, okay, so 12 plus 5 equals 17. So this is going to be equal to 17 over 6. Okay, minus 5 over 18 times yt minus 1. Okay, so that's the regression model that you're going to get afterwards. Okay, so that's a solution basically to it. All right, you understand this? And suppose I have basically, I add another column here, and that column should be, let's say, yt. Okay, yt hat. So this is the basically the explained part of y. Okay, so the explained part of y. Okay, so here you have basically no observation, right? So what you have to do is you put these observations yt minus 1 into the formula. You understand? So that's all you need to do. All right. So you put 0 here and there. I mean, let me just calculate this. So this is going to be 17 over 6 minus 5 over 18 times 0 for the first one. Okay.
The results last week was the constant is 32 over 9.
32 over 9. We had something else.
Yeah.
I got a wrong result then. Are you sure?
Yeah, we solved that, I think, last
Okay. All right. I mean, I can't remember. I had a different result here on my notes card. Okay. But the slope is correct. Slope is correct.
Yeah, the other is correct. Just
Okay.
something else.
Okay. Are you sure? Because. Okay. So that was what? What did you say?
What was it? 32 over 9.
32 over 9. Okay. Okay. I hope it's fine. Okay.
I hope so.
32 over 9, maybe I have to recheck it again, so anyway. I think, but that was the original one. So this is this correct then? The observations here?
Yeah, I think that
Okay. So then the mean, okay, so what would be the mean here of that? So the mean here of this one is going to be 1 over 5 times 3 plus 5 plus 2 plus 0 plus 5, right? So that was the mean of the first one. Okay. I have 3 here. Is that also what you have?
Yes.
Okay, so that's all the same, right? Okay. Okay, now good. Okay, I trust in you on that. I don't know why why I have something else. Okay, so I apologize in that case. Okay, so however, 32 over 9. Okay, minus 5 over 18 times 0. Okay, so then you gotta get basically here the same thing. So 32 over 9 minus 5 over 18 times 3. That's going to be basically the part of the observation yt that is explained by its previous observation. Okay, so that's going to be the part. Okay, and so forth. So this is how you would do this. Okay, so you would plug it in here, and then you would get that as a result. Here for 5, I mean, it's also the same. So this is going to be 32 over 9 minus 5 over 18 times 5, etc., etc. Okay, and so forth. So this is what you're gonna get. Okay. All right. You understand this? Okay. So then basically, I mean, the coefficient of determination, okay, is gonna be the variance, okay, of that sample. Alright, so the variance of the sample, let me just use a different color. So here you have the variance of the sample, okay, divided by the variance, basically, of the total observation. So here you have, this is the variance of yt, but again, only for the 5 observations here. So that's only what you're going to need to consider, okay, because you just have 5 observation pairs, guys, okay? So that's going to be the coefficient of determination. Okay, so the variance of the explained parts divided by the variance of the total parts. Okay, so this is what you're supposed to consider. Okay, all right, and that is of course equal to the correlation coefficient. Okay, I wanted to add this here to it. So basically, if you have a multiple regression model, okay, then you have no choice but to calculate the coefficient of determination just like this. Okay, so for the simple linear regression model where you basically just have one explanatory variable, okay, so basically here this part you just have one explanatory variable, you can use the correlation coefficient, okay, for a simple linear regression model. I think that you're supposed to be familiar with that. But if you're, I mean, if you don't have just like a unique explanatory variable, okay, so you have multiple ones, so then you have a multiple regression, so then you need to calculate the coefficient determination like this. You don't have no other choice. The variance of the explained parts divided by the variance of the total parts. Remember that? Because this is how it sums up, okay? So that's what you're gonna get out of this, okay? I will check my results, okay, because if that is wrong, that's supposed to be also something else wrong, okay? I hope that this is not gonna be the case. Can you maybe tell me what the covariance was? Okay, so what was the covariance of the two? So what was the covariance? What I mean is the covariance of the process yt and yt minus 1. Okay, so what was that?
-1.
No, that was -1. Okay.
Yeah, I think so, yes.
Okay, yeah.
This is correct.
Yeah. Okay, so do we have the 2? Okay. I have a 2 here. So what about the variance of the explanatory variable? The variance of the explanatory variable supposed to be 3.6, right? Okay. So dividing the two results in the basically in that thing. Okay, so and then the coefficient v is going to be equal to the arithmetic mean of the dependent variable minus the estimate for a times the arithmetic mean of the explanatory variable. Okay, so here in this case you would have the arithmetic mean of the dependent variable was equal to 3, and then you have minus 5/18 times the arithmetic mean of the explanatory variable, which is equal to 2. Okay, and then you got 32 over 9, right?
Yeah.
So that's what you got there. Okay, so this is going to be 10/18. Okay, which is basically 5/9. So 5/9 plus 3. Okay, so 27 equals, yes, 32/9. Okay, you were correct. I got a wrong result here for whatever the reason that is. Okay. Okay, so I was just checking it. Okay, right now. No, that's fine. Okay. So basically, that's how you would calculate the coefficient determination on a regular basis if there were multiple explanatory variables, so that will result in a multiple regression model, but you don't. So that's what you that is something that you don't need. Okay. Now you're all familiar with the multiple regression thing. Okay. Do you remember this? I mean, a general case. Maybe we can recall that too. Okay. So what about the multiple regression? Okay. Okay, so you might need this for implementation. Okay, so basically what you have the dependent variable, I call this y. Okay, and you have basically, so beta 1, okay, plus beta 2, or let's say beta 0. That's a better notation. Okay, so that's what we, for the concept. Okay, so we start beta 0, then plus beta 1 times. Okay, so then here you have I. Okay, so this is the ith observation. So this is beta 1 times xi1. So this is the ith observation of the first explanatory variable. And then you have beta 2 times, okay, so beta 2 times xi2. This is the ith observation of the second explanatory variable, and so forth. Okay, then you have beta k times xi capital K. So this is the ith observation of the kth explanatory variable, and then of course you have a noise. Okay, so that's where it starts. Okay, remember this? And basically, I mean, you would have that you define some vectors. Okay, so the vector y is going to be the vector that contains all observations of the dependent variables. So here you have basically y1, y2, etc., and yn. So you have n observations. Okay, and this is yi here, epsilon I, sorry. So, and then you have basically, okay, so the matrix X, okay, the matrix S, I mean X, I mean the first column of the matrix X consists of these ones, okay, and the second column consists of the observations of the first explanatory variable. So this is basically what you have. So this is going to be the first observation of the first explanatory variable. This is going to be the second observation of the first explanatory variable, and so forth. And this is going to be the nth observation of the first explanatory variable. Okay, so that's how it works. Okay, and okay, so then you continue. So here you have basically the first observation of the second explanatory variable. This is going to be the second observation of the second explanatory variable. And here at the bottom you will have the nth observation of the second explanatory variable. So that's how it's basically constructed. Okay? Then you go on. Alright? So then the last one is going to be as follows. So here you're going to have, this is the first observation of the kth explanatory variable. This is going to be the second observation of the kth explanatory variable. And here down there you're going to get the nth observation of the kth explanatory variable. So you have a column of ones, okay, and each column here you have the corresponding observations of the corresponding explanatory variables. Okay, so that's how it's collected. Okay, and I'm going to define here basically the vector beta. Okay, and beta contains basically beta 0, beta 1, okay, so and so forth. So here you have beta k, so you have the corresponding coefficients. Okay, so you have k coefficients regarding the explanatory variables, and then you have also a constant in the regression. Okay, so that's how it's constructed. Okay, now here the Ols estimator. Okay, so that's something that you might consider. Okay, so for implementation. Okay, so the formula for the Ols estimator is of course the transpose of x times x. Okay, that's the first product that you calculate. Okay, then you invert the matrix. Okay, so x transpose times x, and then you take the inverse of that. Then you multiply it by x transpose times y. So this is going to be basically the formula how to calculate the estimators. Okay? Alright? Remember this? Okay? So after doing this, how would you, I mean, when you calculate these, okay? So then basically you would get the explained parts, okay? So the explained parts of y by just multiplying x by the estimates, okay, that you would get. So then you will get the explained parts as a sample, okay? So that's going to be the sample here, okay? So what I'm having is going to be the sample here of the explained parts that you see here, okay? If you want to calculate them, okay? So that's what you would get afterwards, okay? Now, if you wish to, let's say, to estimate, okay, so sigma square, if you wish to basically to estimate the corresponding variance, okay, of the white noise. So this is the estimator of the variance, okay. So then you have basically you have 1 over n, and then you subtract the number of estimators here in this model. So basically you have k coefficients for the explanatory variables, and you have an additional one. So basically you have n minus k minus 1. Okay, so this is these are the degrees of freedom, okay, for this estimator. And then you have what? Basically you have, I mean, this is the corresponding sum that you get. So basically you would do is, okay, so you have the vector y minus the explained parts of y. So then you basically have the unexplained parts. You take the transpose of them, okay, and then you multiply that by y minus the explained parts of y. Okay, so that's how you would get, okay? And this is, maybe remember this, okay? This here is the residual sum of squares, okay? So the residual sum of squares, that's how you would get it, okay? So the sum of the squared unexplained parts of y, okay? So if you subtract from the vector y, which has the total parts minus the explained parts, then you take the transpose of it and you multiply by itself, then basically you would get the sum of the unexplained parts of y, which is the residual sum of squares. And if you divide the residual sum of squares by n minus k minus 1, where k denotes the number of explanatory variables, okay, so k is the number of explanatory variables and n is the number of observations, okay, observations for each, then this is what you would get. All right, so that's basically the formula, okay. And if you want to, let's say, compute the standard errors for each coefficients, okay. So if you want to calculate the standard error of the coefficients, let's say beta j, okay, so the estimate of the variance of that coefficient, okay. So then you do the following, okay. So then you take the estimator for the variance of the error term, and then you multiply it by the ith or the jth diagonal of the matrix. Okay, so basically here you have x transpose times x to the power of -1. Okay, so that's the inverse of the matrix, but you don't take the inverse of the matrix, you only take the ith element of the diagonal of the matrix. You understand? So I call this JJ, right? So this is the element of the jth row and the jth column of the matrix. Okay, and that's how you would get basically that coefficient. You understand what I'm saying here? Okay, so basically let me just add a little example, so I'm afraid you don't. Okay, so let's say you have a matrix A, and here you have basically 1, 0 and 2, 2, 3, -1, 5, 7 and 8. Okay, so then basically you would have A1, 1, which is the element here on the main diagonal. This is going to be equal to 1. A2, 2 is going to be equal to 3, right? And A3, 3 is going to be equal to 8. You see this? Okay, so if I say JJ, that means that you take the jth element from its main diagonal. Okay, you understand this? All right, so you take the jth element of this main diagonal and multiply that by the estimator for the estimator of the variance of the error term, and then you're going to get the variance basically of the coefficient Bj. And if you take the square root of that, then you're going to get the standard error. Okay, so that's how it works. Okay, you understand this? So then this will be the standard error. Okay, and here, and of course, okay, so the square root of this expression will be the standard error of the regression. Okay, and the square root of this one will be the standard error of the corresponding coefficient. Okay, so the standard error of the coefficient, let me just define it like this, because this is something that you see here. The standard error, bless you, of the coefficient Bj is going to be equal to the square root of this expression. Okay, so this is the square root, okay, of the variance, or the estimator of the variance of the coefficient. Okay, so this is what you want to get. So I will use SE for denoting the standard error of the corresponding coefficient. Okay, you understand what to do? Okay, all right, so maybe you wish to. All right, so I mean, of course, in your assignments, you only need to have a first-order autoregressive process. Okay, that's it. So not a big deal, but it could be the case. I mean, I'm not going to do this, but you could basically generate this for a higher order, or generalize this, sorry, for a higher order autoregressive process as well, if you like, and you would just use these formulas. Okay, so that's the formulas that you would basically apply here. Good, but now I'm going to continue, so that's supposed to be clear. All right. So for the multiple regression, part. Okay, let's continue, guys. Okay, so this is what you were doing. Okay, now, okay, so let me just go back here to it. Okay, so let me just consider the following example. Okay, so basically, I mean, an example for that is, let's say, for instance, you wish to estimate, I mean, suppose that y is an autoregressive process of order p. Okay, so if y is an autoregressive process of order p, then basically you would get that yt is equal to the constant plus, and then you have a1 times yt minus 1 plus a2 times yt minus 2, right? Plus blah 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 plus a, okay, so here you have ap times yt minus p, and then you have the noise. Okay, so that's a representation. Now, if you want to estimate these coefficients, okay, so I'm talking about these coefficients here, right? Then you would have to apply a multiple regression model. So that's what it basically looks like. Okay, so these are the explanatory variables. Okay, so you have the number of explanatory variables is equal to p, and then you have the constant still. Okay, so p plus 1 is going to be equal to the number of estimated parameters. Okay, so now if you want to apply, suppose that, let's say, y is stationary. Okay, so if y is stationary, okay, then this is going to be relatively easy. So then basically what you would have is that the estimator, okay, so the estimator of the coefficient j, or the jth coefficient, I'm not interested in a constant, okay, I'm only interested basically in these coefficients here, minus basically the corresponding true value. Okay, so again, a hat is the estimator, and a is going to be basically the true value of it, divided by the standard error of the coefficient. Okay, so the standard error of the coefficient, okay, is going to be following the normal distribution asymptotically. Okay, so as a sample size increase, okay, so that will converge to the normal distribution, or in particular to the standard normal distribution, of course. So the coefficient, these are the test statistics. Okay, again, so this is also a formula for you guys, okay, because you need to implement the test statistic. Okay, so this is going to be the test statistic of the coefficient aj, right? Of course, for the test statistic, sorry, for the test statistic is basically that you have that the coefficient is 0. Let me just correct this, apologize. So the test statistic, okay, of the coefficient is where you have basically that this is going to be equal to 0. Okay, okay, so that's a formula for this. So basically you test for 0. Okay, all right, so that's a standard error of the coefficient. I'm not sure whether or not I used the notation a hat or not, but I think I didn't. So, but this is just a standard error of the coefficient obtained from the sample. Okay, now that's a test statistic. So basically you test a null hypothesis that the coefficient is significant. Okay, and if the process is stationary, it will work. But you have to be careful, guys. If the process is not stationary, it will not work. So I think that will be in the next chapter. Okay, so the process has to be stationary. Okay, I cannot put enough emphasis on that. Okay, basically, so if the process is not stationary, then the corresponding asymptotic here will no longer hold. So that means that the corresponding test statistics will no longer follow the normal distribution, unfortunately. So a lot of things we're going to change, and that's the, a common, let's say, characteristic of, regarding time series. Okay, so that's what we're going to look at a little bit closer. All right, but anyway, in a regular case, if everything is fine, so the process is stationary, then these are the asymptotics here, and this is the t-test. Okay, so basically this is how you would do this. Okay, so the null hypothesis. Okay, so the null hypothesis, basically, based on the distribution, the null hypothesis, okay, that the coefficient is equal to 0, can be rejected, basically, with error probability alpha. Okay, so this is something that can be rejected. Okay, rejected with error probability alpha, let's say error probability not greater than alpha. Okay, so not greater than alpha if basically the absolute value of the test statistic, okay, so if the absolute value of the test statistics is greater than the corresponding, and this is what you're going to have here, then the corresponding 1 minus alpha half quantile of the standard normal distribution. You know what the 1 minus alpha half quantile is? Remember this? Okay, so the 1 minus alpha half quantile is basically a number that if you put that into the distribution function of the standard normal distribution, then you're going to get 1 minus alpha half of as the result. Okay, so a capital phi is going to be basically the distribution function of the standard normal distribution. Okay, remember this? Distribution function of the standard normal distribution. Okay, so that's basically the quantile that you can grab. Okay, so and if the test statistic, okay, or the absolute value of the test statistic is greater than this quantile, then you can reject the null hypothesis, basically that the coefficient is equal to 0, meaning that the coefficient is significant. Okay, and that's called, you know, the t-test. All right, so that's the t-test. Okay, I'm not sure whether or not you heard this. Okay, so basically you test the corresponding coefficients. Okay, all right. I'm not using the t distribution here because I don't assume that the white noise is normal. Okay, so that asymptotic holds no matter what. Okay, if you assume that the white noise is normal, then basically what you're going to have is that the test statistic will follow the t distribution with n minus k minus 1 or n minus p minus 1 degrees of freedom. Okay, let me just add here this to it. So this is just asymptotically true. Okay, so if, let's say, if the white noise, okay, is normal, okay, so this is a normal distribution with mean 0 and variance sigma square, then basically you would have that the test statistic, okay, under the null hypothesis, okay, so then the test statistic under the null hypothesis will follow the t distribution with n minus p minus 1 degrees of freedom. Okay, maybe you remember this. Okay, but only if the null hypothesis is true. Okay, so under the null hypothesis that the coefficient is 0. So if the coefficient is 0, then basically then the test statistic will follow the t distribution with n minus p minus 1 degrees of freedom, but provided that the white noise is normal. Okay, so that's only the case. Okay, and of course, I mean, the t distribution converges relatively fast to the normal distribution. Okay, so that's not going to be relevant. So in practice, if you, let's say, I mean, in time series you have probably more observations and you might need. Okay, so that's the asymptotics, or these are the asymptotics that I use in most cases. Okay, you don't have to assume that the white noises are normal. Otherwise, I mean, if you have, let's say, if the number of observations that you have is not large, then maybe it would be a good idea to assume that the white noises are normal. But you need to verify that, of course, too. Okay, so that's not so easy in most cases. Okay, you understand? But these are the asymptotics that you probably are familiar with. Okay, now, on the other hand, okay, so the f-test, okay, so basically where you would examine the significance of the model as a whole, so not just a single coefficient that you would take out, but basically the significance of the model as a whole. So this is the f-test. Okay, and I'm going to use the autoregressive model as an example. So suppose that basically, I mean, what I have here is I have to have that. Okay, so y is an autoregressive process of order p. and suppose that y is stationary, okay? Again, if that is not true, then this asymptotic, that, you know, the following asymptotic will no longer work, okay? So basically the null hypothesis here for the f-test is that all coefficients are equal to 0, no matter what, okay? So all coefficients are equal to 0, okay? So here in this case you have a1 is equal to 0, a2 is equal to 0, and so forth, and the last coefficient is also equal to 0, okay? So the equation is going to be the same, okay? We don't care about the constant because we don't use the constant basically as an explanatory variable here in that setting, okay? So if the coefficients are 0, then basically then the corresponding explanatory variables, which are the lagged versions here of the process itself, do not have any impact at all on the process itself. Okay, and that is also true. Okay, now this is another hypothesis. Now the alternative is basically that at least one of the coefficients is not 0. Okay, so there exists basically a coefficient for which, okay, so the alternative, I mean, this is quite obvious, but this is something that you need to consider. So there exists, okay, a j from the set 1 till p, okay, for which we have that the corresponding coefficient is not 0. Okay, so that's the alternative, but that's quite obvious. Okay, now the test statistic. Okay, so this is the test statistic here in the next section. Okay, so the test statistic is called the f-test statistic. Okay, so the f-test statistic is basically given as follows. I mean, you have r squared, so the coefficient determination, divided by 1 minus r squared, okay, multiplied by, and then you have the following. So here you have n minus, and then you have n minus p, okay. So p is equal to the number of explanatory variables, and then you have p minus 1, okay. So this is the number, okay. Okay. Now, of course, I mean, here you have the intercept is included. So basically, what you have to have is np minus n minus p minus 1, okay. So this is something that you have in the expression, and p minus 1 denotes basically the estimator. So here you just have the number of p, which is, okay, so that would be the general case, but here the intercept is not included, so here you have n minus p minus 1 divided by p. That's the formula. Okay. So don't mix it up, you know, in that expression. Okay. Now, and this is going to follow. Okay, so if, let's say, the null hypothesis is true, then this is going to be, okay, so that converges. All right, so basically, so this, okay, so this follows, okay, convergence in distribution towards the f distribution, and the f distribution has two parameters, and the first parameter is going to be p, okay, which is the first degrees of freedom, and the second one is going to be, all right, so this is what you have, so this is going to be n minus p minus 1 here in this case. Okay, so that's how it's going to work. Okay, so the null hypothesis can be rejected. Okay, so that is true under the null hypothesis, of course. So I forgot to add here this. So under the null hypothesis, okay, so the null hypothesis can be rejected. Okay, with error probability, okay, not greater than alpha if basically the test statistic, okay, so this is the test statistic, is greater than the corresponding 1 minus alpha quantile of the distribution. Okay, So I will denote this as follows. So f1 minus alpha is going to be the 1 minus alpha quantile of the f distribution, okay, with p and n minus p minus 1 degrees of freedom. Okay, so this is, okay, this is the 1 minus alpha quantile, okay, of the f distribution, okay, okay, with p and n minus p minus 1 degrees of freedom. Okay. So depending on how many parameters you have. Okay. So that's a quanta that you're going to look at, and then you're going to, or you can reject the null hypothesis that the model is significant. Okay. I think you have seen this, but I need to make sure that you understand it here. Okay, that's for sure. And now I also uploaded some distribution tables. I don't know if you've seen it. Okay, so then you're going to get the distribution tables. So then you're going to need them for the exercises. Okay, so well, you can check it out whether or not the model is significant or not, or each parameter is significant or not. So then you're going to need the corresponding distribution tables. And what I also uploaded are some literature, okay? Some additional books, okay? I have to take, I'm not supposed to record this, but anyway, so I don't care. You can sue me if you like. So I uploaded these books. I would like you to ask you to download them, okay? And then I would take them down, of course, right? Okay, you're students, so you're supposed to be, actually it's allowed, so, but I don't want to the public basically to have access to it, but you're supposed to have access to it. So your task will be that basically you have to look into the literature, and maybe you're gonna find some examples there, okay? And so depending on basically the method that you want to use, okay, so you look up certain examples and you look for a study that you are interested in and try to repeat it. Okay, and of course it's included by the examples. Okay, so then you can you have, let's say, you kind of orientation regarding your seminar topic that you can write about. Okay, so I just uploaded that for you to check out the examples or just review these concepts that I'm doing here. Okay, but I will add some remarks to it. But I would like to ask you to download the literature and the books, okay? So there are 3 or 4 books, I can remember, okay? You should download them. Good. Now, that's going to be it. So basically what we do now next is we look for the autocorrelation of the residuals. Guys, if the residuals, or basically the error, the white noises here, or the error terms are autocorrelated, then these asymptotics do not work either. So basically you would have to, what you have to do is you have to look for the autocorrelations, okay? So that's going to be the next chapter, 5.4. Okay, so this is going to be detecting autocorrelation. Okay. This is the first thing that I do, okay, when I estimate the time series. So no matter what I do, I test the residuals for autocorrelation, because if you don't, then basically you would find that that the corresponding asymptotic does not hold. So the model is probably is likely to be misspecified. You have to basically add it up. Okay, so this is something that you should do, and I would ask you to do it. Okay, so no matter what kind of model you estimate, okay, you always need to have a test for autocorrelation of the residuals. Okay, so if you don't test the residuals for autocorrelation, I probably assume that the model is misspecified. Okay, so then you can disprove the fact. Okay, so depending on the specification that you use, right? So I will talk about that too. but basically you have to have it, include that into your seminar paper, okay? So please make some notes, and of course I will give it to you, okay? So, but please have the residuals that you observe or that you basically estimate tested for autocorrelation, okay? Now suppose that basically you have the estimates, okay? I mean, this is going to be the correlation or the empirical correlation here for the noises, okay? And let's say the empirical autocorrelation, okay? So the empirical autocorrelation of the noise, I mean, the process is stationary, right? So this will be the following. So this is, I mean, this is supposed to be, you have a sample, okay? So this is basically, you would have that here in the denominator, you have the variance, okay? Again, the process is stationary, so the white noise must be stationary, okay? So if it's not, then basically it's not true, right? So here you have in the denominator, okay, so I call this T, okay, so T is equal to 1 to capital T. Okay, so this is what you have in the denominator, and this is the empirical variance, okay, so this will be the empirical variance of the process, or basically T times empirical variance of the process, so this will be epsilon T minus epsilon bar, which is the arithmetic mean, okay, of the white noise. All right. Now, guys, please note that these are, I mean, suppose that the observations, you had the observations, then the arithmetic mean is not necessarily 0, okay? In a regression model it is, okay? But these are not basically the observations, these are the estimates for the noise, okay? So you have to distinguish between the two, okay? So again, suppose that you have the observations, okay? So the observations, epsilon 1, epsilon 2, epsilon 3, and epsilon capital T, okay? So suppose that you have that. Basically you don't, okay? So in regular case you don't, but suppose that you would, okay? All right, so here you basically have T times the corresponding variance of the process, which is the product of this corresponding standard deviations, and here in in the numerator you have the following expression. So you sum it up from T is equal to 1 until capital T minus H, and of course H denotes the time lag, okay? So that's how you would calculate the corresponding empirical correlation. So what you do is you have the noise at point T minus the corresponding arithmetic mean. You can take the arithmetic mean from the whole sample, okay? So that's what you would do. And you multiply that by the noise at point T plus H minus the corresponding arithmetic mean. Okay, so this is the empirical autocorrelation of the process. Again, this is not the theoretical one, this is the empirical one. Why? Because for the theoretical one, you would have the covariance divided by the variance, right? But that's not what you see. It's basically see here, because these are the empirical analogs, okay? So, and of course, epsilon bar is going to be equal to the arithmetic mean, okay, of these observations here, okay? So that's the arithmetic mean, guys. You know what the arithmetic mean is, okay? So that's how you would calculate the empirical autocorrelation of the noises, provided that you had basically these observations, okay? So provided it is true. This is the empirical analog, okay? And you just ignore the fact that basically you don't divide this by capital T here, okay? So that cancels out. So that's basically your autocorrelation or empirical autocorrelation, okay? So this is the empirical autocorrelation here, okay? Empirical autocorrelation. Okay? Right? Good. Now, what are the basic properties here of the empirical autocorrelation coefficient? And I will summarize this by using the following lemma. Okay? So you can use that to develop certain test statistics regarding tests. Okay? So basically, I mean, let's assume that you have the white noise with the constant variance and this and that. Okay? So basically, you have to assume that the white noise is an IID process. I don't have much space here, so I will start that on the next page. Okay, so let's basically assume that you have a white noise process. Okay, and what are the properties? Okay, so basically if you have a white noise process. Now, the properties are as follows. So basically, or interestingly, you find that if you take the square root, okay, of t and then you multiply it by the corresponding empirical autocorrelation of the process, then you will find that basically that this thing converges in distribution to the normal distribution. Okay, so that basically means that the larger the observations are, okay, so I mean as of course t approaches infinity, okay, so the larger the number of observations are, okay, the more likely it's going to be the case that this expression will be following the standard normal distribution. That's what it means, okay, so this is what convergence in distribution means, okay. So basically so capital T to the power of 0.5, or the square root of t times the autocorrelation, will be asymptotically normal. That's the first thing, okay. That's going to be the first thing. So, and based on that, you could basically test the autocorrelation. So that would be the corresponding test statistic, and if this corresponding test statistic, or the absolute value of the test statistic, is larger than the 1 minus alpha half quantile of the standard normal distribution, then basically you would find that there is a significance regarding the autocorrelation. Okay? Okay, so basically with respect to the time lag h, remember. Okay? Alright, so again, so if the absolute value of this test statistic here is greater than the 1 minus alpha half quantile of the standard normal distribution, then you would find that there is a significance regarding the autocorrelation. But in practice, there is a problem because you don't have the observations, okay? You just have the estimates, and that's going to be the problem. But suppose that you have, then you could use the normal distribution, okay? Good. Now that's the first property that you basically would have. Now, and interestingly, this is also true if you look at, you know, the multivariate case regarding the multi-dimensional autocorrelation. So suppose that you have t to the power of 0.5 and times the corresponding vector. So the vector will be here. So the empirical autocorrelation of the process, okay, at point or 4.1. Here the empirical autocorrelation of the process at point 2 and so forth, and the empirical autocorrelation of the white noise process at point h. Now this thing, okay, will also converge to the normal distribution, guys, but this is the multi-dimensional normal distribution, okay, so this will basically be asymptotically normal. Here you're going to have the mean, which